them are the people who are out there, interested in learning a little bit more.
Yeah, definitely.
Well, and then for a PhD, so just some other like facts students don't often know, you do not need to earn a master's in order to get your PhD. You can
Hmm.
bypass the master's altogether.
Right.
And you can set out to get your PhD and be like, yeah, I thought I wanted my PhD, but I think I'm gonna finish it with a master. So you don't have to do, um, you know what I mean? You don't have to do a master's along the way, and it typically adds a little bit of time. And I really wish more, United States citizens were earning their doctoral degrees. I think we have, I think that U.S. citizens are as talented as anybody coming in from another country, and we deserve to earn PhDs too. So I was the first person in my family to earn a PhD, and now like my son has one. Like all the children think
Hmm.
they have to have it and all that kind of stuff. I'm like, no, you don't need to get a PhD. But so if you guys should both think about it, I guess is what I'm saying.
Yeah,
All right,
definitely.
I can see we're already live streaming, so that means that's my cue to show my slides and to properly introduce myself. So let me share screen, and I want to start the slideshow. Presenter view, start from the beginning. That's what I want. Okay, welcome everybody. My name's Janet Callahan, and you are joining us, and I'm so thankful for Husky Bites. This is season 5, I believe, of Husky Bites, and what this is a free webinar where we learn something new, live Monday nights at 6. And if you miss it, you are able to watch these because they're all recorded and they're available in the library. Just Google Husky Bites Michigan Tech, and you will find your way to them. So my name is Janet Callahan. I'm the Dean of the College of Engineering, and I have sponsored this evening's Husky Bites. Another way to join us, if you're unavailable to join us via Zoom, is to, of course, join us on Facebook Live. On Facebook Live, it's difficult to ask questions. In Zoom, you ask questions by going down to the bottom. There's a Q&A button kind of down at the bottom, and if you type a question in there or a comment that you would like me to read, to myself, or out loud, you just would indicate that there. So I wanted to give you a snow update, and I wanted to show you my husky dog digging in the snow, but here's our update: 182.5 inches
Ooh.
in the 2021-22, that should say 21-22 season. And if you want to have, continuous updates on how much snow we have, just go to posse.com/snow. And to put that into perspective, the 82-year average is close to where we already are. The record high snowfall ever was 390 plus inches, the winter of 78, 79. And I bet you we've got some people joining us who remember that day and year. I wanted to follow up from last week's show on breweries above and below the bridge. I'm attempting to put together a compilation of Michigan Tech alum-owned brew pubs, distilleries, etc. If you know of one, or if you own one, or if you can look up one that you remember, just either send an email with that link to engineering@mtu.edu, or else put a link to it in the Q&A, and hopefully Sue can grab those and put them into a document, because I can feel a blog coming along kind of talking about all of the ethanol kind of manufacturing that our alumni have been doing. And I'm going to give this early call to action that I know that Kyle and Nolan will be doing, but I want you to ahead of time hear this. So there is a website here. I'm going to read it out. It's www.superiorideas.org/projects/Stratus, Stratus. And the background on this is that we're about to be hearing from 2 senior members of the Enterprise team, Nolan and Kyle, who will give a better introduction than I'll be able to do. And so our first Michigan Tech satellite in space was Oculus, and it went off in June of 2019. And then there is Stratus, which is due to launch in 2022. However, we need $200,000 plus to get there because it had, and you guys can correct me later on, but it had been selected and then sat for, I don't know, a certain number of years. And so the components that it originally had that qualified it need to be replaced. And we need, I mean, I've given in support of this. That's kind of why I've listed myself as a sponsor. We need some very significant donations in order to get Stratus into space. So, and now there's Oris, which is a work in progress. And so that's our call to action. Could you please give generously? I want to also mention next week's talk will be on February 14th, which is Valentine's Day. And so thematically, we're focusing on the heart, and we'll be hearing from Hoda Hatoum in biomedical engineering about her research on flow dynamics in arrhythmias, or how can you mend a broken heart. And so with that, it's not time for Q&A yet. I'm going to stop sharing my slides. And I would like to kind of bring it back to Nolan and Kyle. So Nolan and Kyle are joining us this evening. They are both undergraduates here in the College of Engineering at Michigan Tech. They are both studying both mechanical engineering and electrical engineering, which I think it's great. One of them is a senior and one of them is a junior, and they're going to say a little bit more about themselves and about the Enterprise program. But I wanted to just acknowledge that the Enterprise program's faculty advisor is Dr. Brad King, and he was going to be here with us this evening, but he is right now on a plane, and so he was unable to join us. But he knew that Kyle and Nolan could pull this off on their own. And so with that, I'm going to turn it over to you both. Please add a little bit more about yourselves, because I know that Brad was going to have you guys self-introduce. All right, take it away.
Sure. Let me go ahead and pull up the nice presentation that we put together for this. Can remember specific settings.
So Kyle, it looks like you're at work because you're wearing a mask.
Yeah, I'm actually in our Aero lab. It's something that we'll talk about, but it's one of our facilities on campus, and I'll be showcasing a little bit of some of the items that we have in here as a little bit of our presentation. So,
excellent. All right, you have successfully shared screen, and it's in good shape. Thanks.
Wonderful. All right, well, thank you very much, Dean Callahan. I very much appreciate it. My name is Nolan Pickett. I am the program manager of the Michigan Tech Aerospace Enterprise. My goals, or my roles on this program, is to basically manage logistics. That's a lot of what I do. A lot of like background logistics for the program. And I'm also, as you can say, a project manager. So I help manage the project schedules for each of the satellite missions. I help look over the finances a little bit. I help a lot with technical communication, and that's largely to people who help sponsor the program, or to the wonderful audience members like you that we have here. So I'll go ahead and let Kyle here introduce himself.
yeah, hi, I'm Kyle Bruursema. I'm a third-year mechanical and electrical engineer here at Tech. I've been the chief engineer of this program now. This will be my second semester as the acting chief engineer, and I've been on the Enterprise for roughly 2 years now. A little bit about me or my role is that I manage the technical details, I manage our requirements, and I manage building and testing integration of the satellite. I will say that Nolan also has a lot of that technical knowledge too, as building a satellite is a lot of work and is needed to be spread across a lot of people, especially as undergrads as we are.
Yeah, we will get more into how all that stuff is going to work later, but yeah, thank you, Kyle. Well, let me just say we are very excited to have all of you here. This is a program that Kyle and I both love and hold very close to our hearts. In fact, I think it's largely one of the biggest reasons why both of us chose to come to Michigan Tech to begin with. So we are super excited to share you about this. So why don't we go ahead and jump right in. So who are we? We are the Michigan Tech Aerospace Enterprise. We are one of the oldest and largest enterprise programs on Michigan Tech's campus. You can kind of think of an enterprise program as a student-led, almost like a small student-led company within the university that allows students to be hands-on and try certain facets of engineering and get that experience. So more about who we are. We have two primary mission objectives on our program. The first is to educate. This is a university. This is a really cool opportunity for students to learn, and they get to learn about space systems engineering is primarily what we teach. They get to do that through building and designing spacecraft themselves. I know Michigan Tech really likes to promote the hands-on portion of their classes. A lot of the labs are very involved, and you get to do the work yourself rather than just learning about the theories. And that's very much how we like to do things too. You get to be hands-on with our spacecraft.
It's our brand. Michigan
Yeah.
Tech's brand is hands-on.
Yes, exactly. And that actually leads well into our next point here, is that our second objective, we actually solve real-world challenging problems. These satellites we're building, they're not science fair projects. We're not doing them just because the university told us to or because we felt like it. These are actual satellites. They're going to space, and they are relevant to actual U.S. military and NASA needs.
No, and I think I don't know if I had heard you say it or not. How big are we? How many students are we large right now?
We have about 80 students. I think the official number is 78, but yeah, we're sitting pretty good in my opinion.
Mhm.
So let's go into a little bit about where the aerospace industry is at the moment. So in prior years, the aerospace industry was largely driven by motivation from the government and even some military motivations back in like the 1970s or so. So now we're in the midst of something called the new space race, where space has become commercially accessible and is now driven by things like tech miniaturization and lower costs. So over time, technology has advanced so much that our satellites have actually advanced right along with it. Beforehand, satellites used to be the size of large school buses. You can see on this image on the screen here the regular satellite. It's very large. As you can imagine, it costs a lot to make. And now our technology has advanced so much that we can actually take all of that technology and scrunch it down into a much smaller form factor, or what we call a CubeSat. It's very similar to how computers used to take up entire basements, and now you can literally put more power, more computing power in your pocket. And I think that this is baffling.
Nolan, see if you can turn up your volume a little bit. I have
Yes,
in
yep.
thanks. So on
Yeah,
the
I
or
did
else
see
talk
that
louder.
message earlier, and I did turn it up a little bit. How
All right,
is
good.
that now? Am I
I
fairly
it's coming through pretty well, I think, but it was a little quieter earlier. Good. I'm glad you saw that.
okay? I'll turn it up a little
Thanks.
bit more just to be safe. Okay, so before we go on, we have a couple poll questions that we'd like to send out into Zoom. So the first is to actually estimate how much that regular satellite would cost. I want you to think about how much that size spacecraft would cost to produce. Would it be somewhere in the trillions of dollars? Would it be $1 billion? Be $1 million? Or that's just too many zeros for you to think about right now, and that's totally fine. Maybe you just have no idea of how much that would cost. So go ahead and just take your best guess. And I will give you a hint that the next question will ask you about the price of the CubeSat, the smallest one that we have on the screen.
And so the regular satellite would be, I want to say, like, let's do feet, 20 feet by 5 feet.
Oh, I'd say it's even larger than that.
Okay,
Um, yeah,
big.
satellites that were released back in the late 1900s, they were massive. That's primarily because the technology they needed to complete those missions needed to be quite a bit larger than they are now. So, electronics have become so much more power efficient these days, and our computers have just gotten so much stronger that we can shrink them down. Alright, so I don't know if you guys can see the polls like I can.
They sort of
Sure this
can. The ones
works.
who are live with us can, and the ones who are might be watching us later or are on Facebook can't.
Ah,
So
okay.
so let them know what the most popular answer was.
Yeah, sounds good. So it looks like you guys said that you think that's going to cost about $1 billion to make one of those regular satellites. I hope all of you didn't use Google, because I'd be a little upset. But anyways, let's keep going. So let's do that next question.
Wait, were they right?
Yeah, I think they were right, and we'll show
It
that
is $1
answer
billion.
here on the screen in a
Okay.
second. Yep, it's roughly $1 billion. So let's go ahead and do the next poll question. So yeah, how much do you think it would cost to make the CubeSat that you see on the screen there in the lower left-hand corner? $1 trillion, $1 billion, $1 million, or it's still too many zeros? Oh, I have a laser pointer. Can you guys see that laser pointer?
Yes.
No way. Okay. Yep, so that CubeSat right there. How much do you think it costs?
Well, the audience is answering about $1 million as a majority vote, and there's some people who are going for that's still too many zeros.
Yeah. That's understandable.
Mhm.
And I think those people who answered $1 million are happy to know that you are correct. It only takes about $1 million to make a CubeSat, maybe even less.
Actually,
Um,
to our missions, actually, it is a little bit less than that even. Yeah.
mhm.
Ours is sitting right around 600,000, I believe, and Stratus is something similar, a little bit less than that, I believe.
Yep, exactly. So yeah, these spacecraft are now much smaller and a lot less expensive to produce. And the other really cool thing is that technology has advanced so much that these satellites can actually work together to accomplish one goal. So instead of having one massive satellite that costs billions of dollars to make, you can make a bunch of these little satellites that cost significantly less and make them work together as one system. And we call this a constellation. A really good example of constellation is the Starlink satellite system that was sent out by SpaceX, I think a year ago now, something like that. I don't remember.
I'm not sure
Um,
they did either.
yeah,
Nice.
but that's just a really good example. It's a commercial company. It's a privately owned company, not by the government, that are sending up these spacecraft, and they're providing internet to people that may not have access to it as much as others do. So it's just a really good testament to where the aerospace industry is now and how it's advanced over the past 50 years or so. So you guys are probably thinking, man, there's no way that these undergraduate college students who graduated from high school like 3 years ago can make a satellite. Well, I will say that we have. And guess what? It's in space. So back in June of 2019, we launched the Oculus Satellite. This actually went up on a SpaceX Falcon Heavy rocket, and we had a group of alumni and people that actually worked on it in our program go down to Cape Canaveral and launch the rocket launch up into orbit. And the other cool thing is that it was also noticed on the SpaceX live stream. So if you were watching that rocket launch, you could see the Oculus spacecraft on the side of the Falcon Heavy there. That is a screen grab live from that feed. So I think that's pretty cool.
Put your little special cursor on it.
Yeah. So there's the arrow pointing here, and you can see the Oculus spacecraft right here
Oh,
in the
wow.
upper left-hand corner.
Nice.
And then if you look in this picture up here, it's this shape right
Okay.
here.
Well, that made it easy to launch.
Yeah, exactly. And funny enough, we actually do have a video from the launch that we wanted to show you guys, so I'll go ahead and play this for you.
9, 8, 7,
6, 5, 4, 3, 2, 1.
0, 0.
Holy
Oh man, that's exciting. Hopefully that's not blowing your ears out or anything.
Well, if you ever get to go to a launch, I don't know if you guys were there, but it's very loud and the earth rumbles. And it's
Were you there,
very
Dr.
bright.
Callahan?
I was not there for this one, but I've been there for what do we call it? A shuttle launch.
Ah, gotcha.
Or
Oh.
in Florida, yeah.
Yeah, that's really cool. I know Dr. King was there watching the launch, and
Yep.
yeah, I heard it was super
it was
bright
rescheduled
and-
a few times, yeah.
Yep, exactly. Well, now that Oculus is out of our hands and actually off the planet, we have 2 new missions that we are working on. The first of which is Stratus. This is a mission focused on collecting thermal data on clouds to help us build climatology models. And then the other one is ARIS. And this guy is focused on studying the interference potential of satellites in GEO. And then Stratus is sponsored by NASA, while ARIS is sponsored by the Air Force Research Laboratories.
And these clever names are related to their function, right?
Yes, exactly. We'll get into a little more of what those mean in a bit, but they're actually derived from Latin words. Same thing with Oculus. I believe it's Latin for something.
I
should
believe
know
Sights.
this.
Oculus was Latin for the eye, Stratus
Thank
was
you.
Latin for the cloud or clouds, and Aris is for the ear.
Mm-hmm. Yeah, exactly. Let's go ahead and talk about each of those missions. So starting off with Stratus. As I mentioned earlier, Stratus is focused on taking thermal images of clouds. Now, you might be thinking, okay, what do these students need with cloud images? Well, the cool thing is that we can study these clouds to better understand climate change on the Earth. Clouds largely affect the radiation coming into and out of Earth's atmosphere, and that in turn has an effect on the climate change that might happen throughout the planet. So what we can do with Stratus is take images of these clouds from multiple angles, stitch them together, and create these weather models that'll help us understand how these clouds are going to work. So moving on into how we plan to do that exactly, we have 2 primary mission objectives with Stratus. One is cloud fraction and the other is cloud top wind. Cloud fraction is basically taking an image of the cloud and measuring the amount of pixels on the image that could be potentially a cloud and differentiating them between things like light from the surface and things like that. So if you see in the render on the lower right hand side of the screen here, right there is the camera. The big circle is the camera, and that'll be taking those images for us. And then the second mission objective is cloud top wind. So what we can do is actually take pictures of clouds. So say this is a cloud here. We can actually take a picture of it from multiple angles, and from that, like I said earlier, we can stitch them together to figure out the speed at which the cloud is moving and the direction. And if you remember from physics, it gives us a very nice velocity vector of where those clouds are going. So putting together how large they are as well as their velocity, we can make these weather models of the clouds. And just some other motivations for why we're doing the mission. There are other spacecraft in orbit that can do similar things. However, we are shooting to make these weather models at a much smaller cost. As I mentioned earlier, these small sats, these CubeSats, are a lot cheaper than traditional satellites, and we want to be able to use a whole Stratus constellation to make these weather models. Cool. Alright, now let's talk about ARIS. So ARIS is primarily focused on exploring the interference potential of satellites in GEO. Okay, what the heck does that mean? So when we say interference potential, we mean 2 ways of potentially interfering. So the first is electrical interference. So as I mentioned earlier, space is a lot more commercially driven, and it's a lot cheaper to get things into orbit. Having satellites be smaller means that they have less weight, which means that they take less rocket fuel to get into orbit, and it's cheaper. That being said, it's easier to get technology into space more than ever, and that means we also have more things in space now more than ever. Because of that, all of these satellites are trying to communicate to the ground by sending signals to the ground by downlinking. And because there are so many spacecraft in orbit, there's a potential of these signals interfering with each other. So one ground station might be trying to talk to that satellite, but a satellite just a little bit past it is actually shooting signals to the same area, and that creates problems for communication. This is really similar to if you're ever driving down the road in your car and you are listening to the radio, and then you start to go in between radio stations and you get like a bit of static. That's very, very similar concept to what's going on here. So that was the electrical potential interference, and then the other I want to talk about is physical interference. As I mentioned, there's a lot of things in space right now, and when you get a lot of things starting to cluster together, that creates the potential for them to actually start hitting into each other. And I'm sure you know that with cars, that's not a very good thing. Again, going back to the car analogy, it can cause damage to the body. It can cause damage to the function of the car so that it can't move anymore. Same thing with satellites. If a satellite gets damaged, it's really hard to repair them. So, say a solar panel gets broken, then the satellite can't get power, then the satellite basically won't work or send signals, and then the mission's kaput, right? So this is another really big concern that we have moving forward into the future. And both of these things will be explored through the ARIS mission in some really cool ways. So the first way we're going to do that is through this is beam mapping. So this will address the electrical interference portion that I told you about. So what's going to happen is that the ARIS spacecraft will fly in low Earth orbit. It's going to fly below our target satellites and fly in and out of the beams, the signal beams that those satellites produce. This yellow triangle you see here is the signal beam. So as it moves through this beam, it's going to measure a few things. One, ARIS is going to take in the signal from the target satellite and measure that satellite signal's power. And as it does so, it's also going to take a timestamp of that power collection, as well as the GPS position of the ARIS spacecraft at that time of that collection. So once it takes those measurements, it's going to perform some onboard processing using our components. So we will then, we have the GPS here that will move data down to our onboard payload, which is basically the components on our satellite that do the mission science, that perform this mission analysis. And then they will downlink this information back down to the ground. And here on the ground we can make what are called beam maps. And these maps can actually tell us where these target satellites are sending signals to, and even how powerful they are. This has a lot of really cool implications. Basically allow us to figure out what these satellites are doing in orbit. You can see that as our spacecraft moves through orbit, it'll make this waffle pattern like you see in the upper right hand corner here, and we'll start to put together this image of what these spacecraft are doing and where they're sending signals.
One really cool thing to know about this beam mapping objective that we have is that there is currently no known satellites that we know of that are doing this objective, that are doing it through space. So this cost-effective idea that Nolan was talking about earlier with using small sats also applies to this as well, being that the only other way to do it is through ground receivers, flying either a plane or driving around with a car on the ground to pick it up. And although that might seem cheaper in the short run, in the long run, when you tend to drive a car around or fly a plane around, it takes a lot of man hours and it takes a lot of fuel. And so this is a good way to save on those costs, is to having one large time cost of a satellite that would, over the span of say 20 years, do the same effect. So
Yeah,
much more effectively at that.
Yeah, instead of having to refuel a plane, instead of having to pay someone to drive it, you can just throw a satellite in space and call it good, right? So anywho, like I said, that is the first mission objective that deals with the electrical potential interference. Now the second part to this is the physical interference, and the way we plan to do that is through utilizing something called multilateration. So as I mentioned earlier, the ARIS spacecraft will be flying between the target satellite over here and the Earth, as you can see here. And as it does so, it'll pick up the signal of the spacecraft. We don't know where that spacecraft is. We don't know anything about it. All we know is that it's emitting a signal. And what we can do is use something called time difference of arrival to actually calculate where that satellite is in orbit. So we have our ARIS spacecraft here, we call that one receiver. And at the same time, we're going to have 3 other, we call them signal receivers, on the surface of the Earth, getting the same signal from the target satellite. And what we can do is use the difference in times between where the ARIS satellite is and where the ground satellites are to figure out where ultimately the target satellite is. And we can do that through some fancy onboard calculations, as you can see on the bottom here. This will actually give us an approximate ellipsoid. It's not going to give us an exact point in space to where the target satellite is, but we are going to produce an ellipsoid of confidence as to where that satellite may be. So I think this is pretty cool. This is technology, like Kyle said, that not a lot of people are doing. That we're doing it in a way that's fairly unique. And the cool thing is we're just undergraduate students. So very, very exciting stuff here.
It's very exciting. And a big thing about this slide too that's really cool is, I think Nolan had mentioned earlier, we're a Pathfinder mission. So in the future, if another, say, company wanted to kind of reiterate what we're doing here, they would take those ground receivers and make a constellation of satellites out of them that could do the same effect. Actually, probably a little bit more accurate than what we're doing. Because we're a student organization, we can't fund 4 satellites ourselves or build 4 satellites because that's a lot for us. But it is something that you can do, and it would be a lot more effective.
Yeah, that's a really good point. Ideally, we'd want these 3 receivers right here to be in space. They'd be ARIS satellites, just like this one right here. We'd have 4 ARIS satellites, but we really don't have the manpower or the funds to do that, so we're putting together these ground satellites here. But yeah, this mission is just to test that this system works and that we can do this moving forward.
Very interesting.
Yeah, thank you. And the people at the flight selection review seem to think so as well. So the ARIS mission is part of a, you can kind of think of it as a student program or contest that is called University Nanosatellite Program. And we are in this program with 9 other schools. And basically we were to go through the design phase of the spacecraft and then present it. And then past that, a few schools would be selected to move on and receive funding. And Michigan Tech was one of 3 schools chosen to continue into the next phase of development, which is super exciting. We went in August all the way down to Albuquerque. We had like a 33-hour van ride or something. We took Michigan Tech vans down all the way to New Mexico, and it paid off in the end. So this means that in the future we're going to take the design that we worked so hard on, we're going to refine it a little bit and actually go and implement it. So we're going to go and buy the hardware that we chose, and we're actually going to go stick it all together and make it work. We're going to continue to receive funding from AFRL, or Air Force Research Labs, who are main sponsors for the mission. And then we have also been guaranteed a launch opportunity, which is one of the most exciting things about this, is that we've been told that we are supported and have an opportunity to go into space. So this is super exciting and something that we're really looking forward to here.
What's the timeline of when that might be?
It's largely going to depend on our stakeholders and sponsors, but we're thinking sometime within the next 5 years or so.
Mm-hmm.
So we just wanted to show you guys a couple other things about the event. So right here, you might recognize this picture from some of the social media posts, but this is our engineering model of ARIS. This is the model that allows us to, take the things that we made in our computer models and actually bring it to life. And this is what we presented to the judges. So as you can see, it's about the size of a shoebox. It might be hard to tell from this picture, but this is an entirely aluminum structure. We have, I think this is FR4 panels on the side. We can see solar panels here on the top. This is these aren't real solar panels. These are just the ones that we use to demonstrate, where they would be on the spacecraft. We have a couple antennas here. This is a 3D printed antenna, and then up here we have a real signal antenna that would receive the signal from the target satellite. So this is really cool. We had an entire booth set up where we had this on display, as well as a bunch of posters, as well as all of our satellite electronics laid out flat and actually functioning for the judges. Kyle, that big black thing right behind you, that was also there. That's called our electrical ground support equipment, which I'm sure Kyle will go over more later.
Definitely will. I'll be able to
Yeah.
talk about that.
So the other cool thing is that this was just one part of our booth. At the review, we had to demonstrate our technology to a panel of judges and show them that it works. The other cool thing is that we had another group outside doing the same thing, and I'll let Kyle explain this one because he's actually here in this picture.
Yeah, yeah. So what's really cool about this is we were the only group when we went down to New Mexico that said, you know what, let's take our experiment outside and prove that it works. So this was something that was super cool, and it was a really big move for us to actually do this. And so as you see on the right there, Nolan can probably point it out right next to me, is the payload antenna. That is what's doing our science for ARIS. And we actually decided to stick it up, point it at our EchoStar or our target satellite, and receive a signal from our target satellite, proving our mission right there and there on the ground. And then the idea there is that that antenna is flying all around space, collecting more data, obviously, than just one point on the ground. And that was something that we were able to prove our mission science with. It was a super cool experience, and it was super nice there in Albuquerque too. The weather was great.
So
Yeah.
that's a sunshade. That's up there to protect your components from too much sun, probably.
Oh, that's that chair?
Yes, yeah, it's the protect the components from sun, and just in case there was a little sprinkle at all, which there was not. It was a beautiful day. Also to protect us a little bit from sun too. The review got a little. It was super hot. I actually ended up having a bit of a climate change attack with like my I got a little sick on that trip. I actually took an ER trip because I got so sick because of the climate change. I was so used to the northern that we have here that my body just didn't know what to do with it.
It was too hot.
It was just too hot. Yeah.
It was hot, and then there's also a pretty massive elevation change, which I think was,
That was the major
Main
part of the
reason?
issue, was the
Yeah.
elevation change too.
yeah.
I've never really left Michigan all too much. This was a super fun trip for me, so I was super stoked about it.
Yeah. Anyways, let's keep on going here. So a couple other things that we did at FSR, we gave a nice presentation to a panel of experienced aerospace judges. That right there in the pictures, our student advisor, Matthew Sietzema, he's presenting the ARIS mission. And then, of course, we have the nice handy-dandy plaque that was awarded to us, and that's on display down in our Aero Lab. So this is a very fun trip for us. Oh, I think Kyle's going to go grab it. Yes, that guy. Yep, very proud of that. So yeah,
You
we're
should
very, yes, yes. This is a good experience for all of us. I know I learned a lot about the aerospace industry in general, and we're just super excited about it.
We're very proud of you too. All of the alumni out there. You got about 200 people listening in.
Oh, great. Thank you, guys. All right, so before we go any further, I want to go ahead and give out one more poll question. So I know that our satellite names are slightly confusing, with them being from Latin and all, and it might be hard to tell which satellite does which. So I wanted to go ahead and see how much you guys are listening. This question says, what is the name of the satellite mission focused on gathering thermal images of clouds to develop climate models? And you have 4 different choices here. You have ARIS, you have Oculus, Stratus, and you have Starlink. So let's see how much you've been listening.
I think they've been listening.
Yeah, I think so too. Most of them are going for Stratus.
Yep. Or they know their clouds.
Yeah, yep, exactly.
Or they're Latin.
Yep, right.
Very good.
Cool. Good job, guys. Yep, so we got a 78% for Stratus, and then ARIS and Oculus are our other 2 satellites, and then Starlink is one from SpaceX. So that's not even ours. Alrighty, so let's keep going. I'm actually going to go ahead and let Kyle talk here for a little bit. So we've talked about these really cool satellite missions. Now we want to actually talk about how we go about, doing them and executing them. So Kyle, go ahead and take the floor.
Yeah, absolutely. You can just click to the next slide. So how do we build a satellite? Well, to kind of get the idea here, we're an undergraduate student program, as Noel had mentioned, so we're all undergraduates here. So a lot of what we do is actually learning and going about it, following the NASA guidebooks, following the SMAD, which is the Space Mission Analysis and Design Handbook, and also following the guidelines from our sponsors and stakeholders. And so a lot of it comes down to learning. And before I even get started on how we build it, I wanted to preface that because even for me, this is still my second semester as an acting chief engineer, and I learn a thing every day. There is something I always learn. I probably about 10 things I learn every day. These systems are extremely complex, even though they're packed into a tight package, and there's a lot of things to learn about them, including the science that actually goes into each different sub-team. And we're going to talk about the sub-teams a little bit more in the future as well on the next slide. But on this slide here, I guess we can start off with just defining how we actually come about with the idea of a satellite. So that is the first part there that you see is the mission definition. For RS, that is the mission objectives that Nolan was talking about, which is finding and hearing or getting a signal from a target satellite. Or for Stratus, that's taking the thermal images of clouds. And both of those come with different stakeholders, sponsors that have these problems that they're looking at in the real world and saying, hey, we need somebody to solve these. And so we go, okay, well, we're doing it. We're building things for space. Let's go ahead and solve this. So we go ahead and we pitch our idea to them, and it kind of worked out. For RS, that was with FSR pitching it to your stakeholders, and that's the competition that we won. We sold the idea and making sure that we have the right idea, the right system set up to solve this problem. The next thing that comes is after you have this mission defined and have these things ready, you need to set the requirements, the grounds for them. That comes with any good systems engineering and building of any sort of project. And for a satellite, it's no different. You need to set up different requirements that pertain to your mission or what you're building. For a satellite, that means there's a couple extra requirements that have to deal with the space environment itself. That means it has to survive going up on a rocket, because that is a very harsh environment for anything to sit through. The rocking, the heat, the shake, everything can damage all those really sensitive components on the inside, so you have to build requirements based around that. And so that's a really fun part of the process of learning in this enterprise as well that we do. After that comes the design phase. And that's where you get to go ahead and say, okay, we've got our mission, we've set it up, we are ready to roll. But we're not ready to build it yet. This is where we have to actually define how we want it to look. This is where we go ahead and we say, all right, now we need to actually figure out what's going to make this mission work. Do we want a small sat like Oculus was, which is a larger size of a satellite, or do we want a CubeSat that can solve this mission? What is the possibilities there? And so for RS, the one that you see on the image or on the screen there, that was saying, okay, a CubeSat can solve this mission. And even then, it goes through iterations of what it needs to. RS currently is what we call a 12U CubeSat. So it's roughly the size of a bread box. But it was originally a 6U, something smaller, and we decided that that wasn't enough to supply this mission. And so the next thing you do is after you decide that, you start acquiring hardware or building your own. Because we are a student-run organization, we don't have the skills or the expertise to go ahead and fully develop a satellite on our own. That means designing the individual cameras or sensors on the satellite or designing the boards that come with it, although we do design some boards. Oculus was built by students fully and thoroughly, actually designing each part of it. But that's something that took a long time to do and something that we wanted to focus more on the actual engineering, the systems engineering, and learning how to build a satellite rather than building those individual components. So anyway, that's just something simple about it. But we go ahead and we acquire these hardware and we put it together. And so that's what RS and Stratus are, building of COTS components, space-ready components that are put together. So the last couple things that we have here are the testing and integration, which I'm actually going to touch on a little bit more in a second, and the mission operations. So what is testing and integration? That's as simple as it sounds. We need to verify that the spacecraft's going to work, and we need to verify that we can put it together, and that we put it together correctly is the big thing. And so for RS and Stratus, this is a Stratus model. That means first and foremost designing what we have as a 3D printed model. This means showcasing that first and foremost that we have all the components that we need and that they fit into the CubeSat model. So this is a 3U. You can see kind of size comparison to me. And we made sure that it could fit. This is a real size version of our camera, although it is 3D printed. And these are a real size of all of our components, all put into the, I don't know if you can see, this is an aluminum frame. So we verified that our components could at least fit and we had the right structure built in that one little simple thing. Now there's a lot more complexities to it, but that was one simple way of doing so. So with that all being said, I've mentioned it a couple times here. I want to hit on what systems engineering is just a tiny bit, and I'm sure all of you have heard about it, at least at some point. And that's the concept of taking an idea all the way into mission operations. It is the full process of building a mission. And so for our satellite, we did just that. We defined the mission, which was Ares or Stratus, and set their goals and followed down that list. I think the biggest thing about systems engineering that I've learned so far is that these things are cyclical. There is so much process that goes into how these things reorient themselves, or if you decide that there's something, a problem with what you currently designed, and you go back and you revise it, and you edit it and make sure that the mission can fully succeed the requirements. And that's kind of what that quote says there at the bottom, which is that we will achieve these objectives differently as technology and our understanding of the process and our problem evolve. And that means that, ours going from a 6U to 12U was we understood that the problem needed something a little bit more large. We kind of grew it. So I want to talk about what we're doing right now for the RS mission. So that would be the next slide there, Nolan. We are currently in testing and integration for RS. We are currently in the process of going into the clean room, one of our facilities, and testing to make sure that these components work together and that we can integrate them. So on the right side there, I can't actually point to it on my own, or the left side, excuse me, is our CAD model, our structure. And so that originally came down to something that started with this. This is our RS 3D printed model. So you can see RS is a little bit bigger. This is a 12U, whereas Stratus was a 3U. And it originally started with that CAD model, and we wanted to make sure that it worked in a 3D printed version, or we wanted to know the size of it. And so you take it, you go from the model that you make in CAD or structures, or in CAD or any sort of design software, and you first then make sure that that model will actually be what it needs to be. And then you go back and you revise it if there's anything different. Even from a 3D printed model, you can learn a lot, and that is for a space mission, such as wiring. I mean, wiring is a complex beast inside of a satellite since it's so small, and that's something that we learned from this 3D printed model and updated our CAD with. That's just part of the process of testing and integrating. And so on the right side there, then you see all of the things that we're doing right now. The left picture there is of us at a satellite fabrication course, and the bottom board there is actually one of the boards that we designed in that course. That's underneath a UV light that's showcasing its when it got its code on it. On the right side there is our two pictures of our testing. The top one is our clean room. So we have TTC members in there, or telecommunications members, testing their radio, actually. It is on that board, although it's hard to see. And they're essentially just trying to run through and make sure that they can talk to it and make sure that the commands work with it. And below that is more of our payload testing that you'd seen earlier. And so I wanted to wrap this whole part of like spacecraft development up is just by saying that we build this thing from start to finish with our mission. It's that entire timeline that you see on there. We defined it, we set the requirements, and we started building it. We actually, even part of our testing is building things that test it. That's what this EGSE here is it connects to the satellite and helps us test it. It showcases different values for thermistors on there, so thermal readings. It showcases the satellite's commands or how we're talking to it. And it has its own radio on it, so we can talk to the satellite wirelessly. It does a bunch of different actions that allow us to verify the satellite while it's on the ground, essentially. And after that, you need to make sure that it can survive that environment, and that's environmental testing. And that's something that we also do in-house, which is just kind of really showcasing the satellite's ability to work in space. Anyway, I think I've taken enough time on this one. Sorry about that.
Oh, you're good. Dang it, thank you very much.
But yeah, so if there are any questions, I'll be sure to answer them at the end too.
So we've got 35 questions. Some of them are just kind of comments, but
Oh boy.
yeah, we're gonna need to wrap it up, Nolan, and
Yeah,
answer some of these
definitely.
questions.
Let me shoot through the last few slides we have. So we have a few fun facts we wanted to share with you guys. The Enterprise is about 21 years old. We've had 400 plus students come through. We have 12 different majors here, anywhere from mechanical engineering to computer science to, I don't know, chemical engineering. I know we have even physics. So a lot of really cool students come through here. We're all undergraduates. We're well funded. We have a really cool alumni network. I'm sure we have some alumni watching this call right now. And most importantly, we have one satellite in orbit and then also one on the way. Let's see, we have a lot of things that our students can learn about, mission sciences, business even, modeling, hardware, a lot of really cool learning opportunities for our students here. And of course, we have, like I mentioned earlier, a very extensive alumni network. I'm sure you recognize a lot of the aerospace logos that we have on screen here, but these are very well-known companies in the aerospace industry, and we have alumni at all of these companies. So we're very thankful for the students that we've had come through, and we're really excited to see where they go in the future. So with that, I will go ahead and leave it to questions. I know I see 38 questions now. So at the
All
same
right.
time, I'll also let you guys to enjoy this really pretty render of ours here. So yeah, let's go ahead and dive into questions.
Well, and while people are, why don't you go ahead and sort of start selecting the first question you want to answer, Nolan? But I'm going to do another plug for these students' project. So they're the second small satellite, which is the Stratus, needs about $230,000 worth of new components. And so I don't think we're going to be able to raise that tonight, but if we were able to, that would enable that particular small satellite to be launched. And so if you would like to give to that, the link to give to is listed in the chat. So you should be able to just directly link on that and give. And your donations are a donation to Michigan Tech, and they are treated as such. So they've achieved $13,387 against the $250,000 goal. And I just want to thank everybody who has given. I know I've appealed to a couple people directly, and I thank you for that. All right, Nolan, to the questions. Do you see a question you would like to answer? And then
Sounds good.
while he's answering one, Kyle, you pick out the next one.
Yep.
Alright.
I can go ahead for a first here.
Yeah, go for it.
I'm seeing a question from Patrick. It says, what info is Oculus providing? And that is a great question. It is actually up in space, and it is still providing us info. And it is actually a optical calibration satellite. So it helps us calibrate other satellites in the space domain. And it essentially, as its name suggests, it is an eye. It is there to help calibrate the eyes of any sort of camera in space. And that is the best knowledge I know of it. Again, this mission came far before me. I actually never was hands-on with it, but it is a great question. And if you want more info on that, I'm sure we have a way to get questions to us beyond this.
Yeah, thank you for answering that.
Mm-hmm.
And so you guys should so Bruce wants me to mention, and I'm very proud to mention this, if you haven't heard about Deidre Irwin and her Olympic performance in the individual women's biathlon.
Yes.
So she's done very well. This is the one where I believe they're cross-country skiing and then firing a rifle and shooting targets or something like this. Do I have it right?
Yeah.
I might not have it right, so forgive me if I've
I have no
quoted it
idea.
wrong. But yes.
I did see an article about that. That's super cool that we have alumni in the Olympics. It blows my mind.
Yeah, no, yeah. All right, so a couple people are asking questions about the debris and like, don't small satellites contribute debris, and and what about space junk? So do you want to take a stab at those?
I could take that one, Nolan, too, if you want.
Sure. Yeah.
So that is actually a great question. Something I first asked when I joined the Enterprise was, isn't this just adding to it if we're building more constellations? And the answer actually is no, because of the way that NASA and the government around the world have set up the way that satellites in LEO orbit, or any satellite in general, needs to operate. They give us a timeline in which our satellite needs to deorbit and enter the planet's atmosphere and burn up. And the way they do that is they kind of predict how many satellites are going to be launched in a year, and they tell you when you get your mission, you need to have this satellite deorbit in this amount of time. And so for ARIS, we have it sitting between 400 and 600 kilometers, and at that range, it'll actually deorbit in 20 years. And that way it'll burn up. I think the ISS is actually set to deorbit as well in 2030 into an ocean to get out of the atmosphere, or get out of the space environment. So that is one way that we actually stop that problem of happening.
I saw another one earlier. I think that would be up your alley, Kyle. This is from Jeffrey Stricker. Are there special electrical components rated for spacecraft use, i.e. vacuum, operating temp, exposure to solar mass ejections, etc.? Can you speak to cost versus off-the-shelf components, i.e. resistors, capacitors, etc.?
Yeah, actually, I can. I don't know about the second part. I'll answer the first part of that real quick. There are special electronic components, and in fact, that's why we buy COTS. There are certain things that you cannot have in a vacuum. Real quick, off the top of my head, I believe an electrolytic capacitor is one of them, which is very common in a lot of electrical components nowadays. But in space, you can't have something like that because of the liquids in the vacuum that it has. It'll actually explode and damage the spacecraft. And so, or implode, I believe, is the correct term there. And so there are special things that you need to have ready for space flight. And that's, again, something that we buy COTS. So we buy things that have flight heritage. So that way we know that they're safe for our program and safe for space flight. Although we do have a couple components on ARIS that aren't necessarily COTS. So we have to make sure and verify those ourselves as well. And can we speak to the cost for all the shelf components? Yeah, go ahead, Nolan.
Yep, nope, you got it. I was going to ask, what the heck does off-the-shelf mean, or COTS?
Yeah, exactly. Off the shelf meaning that it is perfectly ready for, or not perfectly ready for spaceflight. It still needs to be integrated into our own spacecraft. But COTS being a component that is already ready for, it has like that spaceflight heritage and it's built for the space environment. Building our own, I believe, would actually be slightly cheaper because there's not the manpower behind it. We would input that manpower. However, the cost difference isn't too much because they've kind of perfected the art of doing so.
Good answer. Here's one from John Sawyering. What is the range of temperatures in which the technology must operate while in space? That is a great question. So before I became the program manager, I was actually on the thermal team. We have a whole team dedicated to creating models for thermal models for the satellite in orbit. And what's cool is that the manufacturers of a lot of the components we buy actually give us safe and dangerous operating temperatures. So what the thermal team does is make a model. They model these components in the software, and they see whether the components are within those operating temperatures or not. And if they are at risk for breaking, if they're too hot or too cold, then they do something about it. They implement what's called a thermal management system. So yeah, that's a really good question.
I'm sorry. You have something to say there? Sorry.
Well, I was going to say there's, as you're answering them, make sure you click answered live so that we can kind of keep track of stuff. And so, yes, Larry has affirmed that Deidre competed in the biathlon, won Nordic skis and shoots a rifle, 15 kilometers of skiing. She finished 7th overall, highest of any American ever.
Wow.
Nice.
Hashtag tenacity at its finest, am I right?
And there's a lot of people thanking you guys for this presentation, so I just want to,
thank you so much. We appreciate it. We love you guys.
We really do appreciate it. We appreciate the time to have in front of you all as well.
Mm-hmm.
So what % of the full satellite cost is the launch service?
That is actually helped covered by our sponsor. I don't know too many details about that, so I know that the money we do get does go straight towards purchasing our hardware and testing it, but when it comes to launch, that's a little bit less in our hands as it may be in a full aerospace company.
And would you repeat who the sponsor is of the AURUS?
Yeah, so AURUS is sponsored by the Air Force Research Laboratories. They're a research and development division of the Air Force.
And Stratus is sponsored by CSLI or the CubeSat Launch Initiative.
Which is a part of NASA.
Yep, which is a part of NASA.
Yeah.
No, it's good. So how long will these stay functional in space? Or let's talk about AURUS. How long do you think AURUS might stay functional in space?
Kyle, you want that one?
Yeah, I can take it. AURUS will stay functional for about a year. Our hope is to conclude mission operations in 6 months, but there is a lot to do with space, and luckily, this mission can take as long as it needs to, as long as it's under that 20-year period. It's just actually getting that mission data and proving our mission actually succeeds is the basic requirement for how long it takes. So hopefully 6 months, but if it has to take a year, we can do that as well.
So there's a couple of questions from people who might be students. I want to take them now. So Kristen, for example, is an interested undergrad student, and the question is basically, can you be in this from any major? And Kristen's a biomedical engineering major.
Yeah, so the cool thing about that is that the thermal team I was just talking about, their team leader is a biomedical engineering student. Um, you do not have to be a specific major to get on an enterprise. We take anyone. These systems are so complex that we need people from multiple perspectives in order to make it function. So we welcome every and all major.
Yeah, and there's a whole lot to learn about that engineering process that not to like our classes teach a lot, but they're always very generalized. The aerospace field itself is a lot to learn as well, and so for me specifically, I mean, I've already learned even in my first semester as just a general member, I learned a lot about the aerospace field that I don't know if I'd learned from my classes unless I took a very specified class. So you don't necessarily need to have knowledge in what you're doing here because that's the purpose of it. It's to be taught and learn how to do it, and then to put it to practice. So.
Yep. You don't have to feel like you know what you're doing in order to do what you do. Let's see.
Well, how has this one been answered from Theodore? How do you keep your satellite oriented correctly?
Yes, that's a Kyle question.
Yes. Okay. Yeah. So I was a previous part of our sub team called Attitude, Determination, and Control. So attitude is the way that I have a satellite right here. I can use this to talk about it. So attitude is in which way the satellite is pointed in space. So that is exactly what you're talking about, is controlling the satellite's orientation. And that is done through, for CubeSats, using what are called the magnetorquers and reaction wheels. So a reaction wheel is actually something that spins and builds momentum. It's basically a wheel on each axis, and these things spin and build up momentum so the spacecraft will actually rotate. And if you think about something spinning this way or clockwise, there has to be an equal and opposite reaction in the other direction. And that's how the spacecraft spins, is that other direction. And then magnetorquers provide that push against the Earth's magnetic field to actually desaturate in that momentum, so that way it can speed up a little bit faster and stabilize it. And those are just the two of the different components that help do this attitude control. Although there are other ways to do it as well, such as propulsion. But we do not have propulsion on our spacecraft.
So there's a big thank you from Gretchen Hein, who's the Society of Women Engineers chapter advisor, thanking you for doing your outreach activity for middle and high school students, and that you're going to be doing it with the Girl Scouts in April. So big thank you from Gretchen. And
so cool thing is that, our enterprise has been working closely with the Society of Women Engineers, and we have an outreach program planned for some local Girl Scout troops that's going to be happening at the end of this month, and I believe in early April. So big thank you to Gretchen for helping us kick that off, and it's been a pleasure working with her for sure. Let's see.
Oh, there's so many questions. We've answered 21. There's 39 open, and
boy.
we're like doomed because we try to call a halt at 7, so we're going to go a little tiny bit longer and stretch it out to 7:05. So
it's okay.
You guys should pick your questions you want to answer, or else I will.
So most of your campus organization could qualify a career at JPL. Maybe. I think I know some people in our enterprise who have worked at JPL.
Yes, we have some actually, I think, going on internship this summer as well.
Yeah, so probably.
Yeah.
I will say that.
I seen one that says, who determines the altitude for satellites? And that is something that we actually get to choose a range for. And that is something that we actually asked the launch provider to do, is to put us into that range. Now, they can decide on at any point within that range to send us off, but at least we get to choose it. And for ours, again, that's 400 to 600 kilometers above the Earth's surface.
Let's see.
Impressive.
Larry asks if your suppliers are working with you as partners, or are they strictly standard suppliers that design to your specs? Yeah, that's basically it. I know our structure, our aluminum structure, is actually machined by what is it? Royale Incorporated in Calumet. Royale Machining.
I think you're right.
Yeah.
Royale.
Yeah. So there's nothing super special about them. There are a couple things that we do to make them space raid, like putting on like a black coating, like anodizing them, or even sealing the boards, conformal coating them, like Kyle said earlier. But yeah, we just work with normal companies, some local, some very much not. Kyle, where are our radios from?
Our radio, GOM space, is from Spain, I believe.
Mm-hmm.
And then we have a couple components from Denmark, some from South Africa, so a lot over the world.
Yes, that's a good question.
So Greg is asking, when will the video recording become available? And so these are all posted. They're posted in two or three different ways. So it's within about 24 hours, and you'll see them on the Husky Bites website. All of these are also posted on the Michigan Tech College of Engineering YouTube channel. And I don't know if Sue, if you can put a link up there. Yeah, she already did. There we go. So the link to where you can find them is posted in the chat. Why don't you have propulsion on your spacecraft?
Yes, that is actually a great question. Again, another question I asked when I was first on the Enterprise, because that's the first thing I think of, how to control a spacecraft. It's because it's not actually too terribly necessary for a spacecraft. First and foremost, the fuel of it is a big thing that would take up a lot of room on a spacecraft and doesn't actually fit on a CubeSat form factor. We don't need to be at a specific altitude to perform our mission other than the ones that we specified. Our mission can perform at any point within that range. So we don't need to have propulsion to boost us out anywhere. Also, we can turn the spacecraft without using it and actually using electrical components, like I said, the reaction wheels. So luckily speaking, propulsion isn't very necessary in a lot of spacecraft.
I didn't know that.
Good question.
Oh gosh. So we're going to take two more questions and then we're going to thank you very much. There's
Sounds
literally
great.
36 open questions.
Yeah.
But I wanted to go back to a question I think a future student or a current student might have asked, which is, do you have to learn some of this kind of stuff in high school, or is this like are you able to learn this here, at Michigan Tech?
You're definitely. I know I learned almost nothing about this in high school, and now I'm here. It's as much as you want to learn. We have a bunch of textbooks up I'm looking at right now, all that guide you through the process. And honestly, I was taught by a lot of just answering questions or asking questions and just learning from prior members. None of it you have to learn throughout high school. If you come in with no experience, that is the exact point. We are here to teach you. Also, in any industry, it's meant to teach you. So.
Mhm. Yeah, I did no STEM stuff in high school. I wasn't in robotics or anything. Then I came to tech and learned everything here just by being curious and asking questions and caring about the things that are presented to you. So no, you don't need to be like a star engineer in high school or anything like that.
Well, and Enterprise is about showing up, right? You meet weekly, and then you're working on things across the week, and you're
Mhm.
working on more and more the more you move up in the Enterprise program. So our Enterprise programs are at, we have a junior here, we have a senior here, but you can join as early as your first year here. And you participate them across multiple years, and then you inherit increased responsibilities as you move up, right? And so Nolan, you're basically in the leadership role. You're both in leadership roles now, so
Mhm.
right?
Mhm.
Exactly.
Yeah.
Yep, you just learn. You learn as you go, and you ask questions. That is the
Mhm.
best way to go. I think we were always told to ask what and why, and the
Yeah.
thing that you're told in high school is there's never a stupid question, and there's really not.
Well, and I wanted to bring it back to Stratus. So we have James asking what parts of Stratus need to be updated before the launch. So my understanding is we're hitting a pretty hard deadline. If we don't have the $250,000, that one probably won't go up in the launch, and we'll divert any funds that were raised to Oris. But so what parts need to be updated in Stratus?
Yeah, I think I can speak to that a little bit further. So Stratus had some fundamental issues when it came to some of its components. Mostly it just comes down to a little bit of vendor miscommunication and what we truly needed. So I guess the major components that we're looking to update are our comm radio, and I think some of our ADCS components, our attitude control components. But for the majority part of it, I think that we're looking to update the whole satellite just so that way we can truly get the mission back on its feet and ready to roll.
Well, and I do want to personally thank, I reached out to several of our alumni to give to this mission. And I just want to thank you. I didn't acknowledge your names because I didn't know if you wanted to be anonymous supporters, but yeah, it's a tremendous opportunity. We're so proud of you. We're very proud of the enterprise, the Aerospace Enterprise. So thank you everybody for joining us. Nolan, do the last words of encouragement.
Dr. Callahan.
I think your mic got shifted up. It's kind of hard to hear you.
Any words of
There we go.
encouragement to future people who want to work on stuff like this?
You can do it. And everybody can do it. If you really want to, you can. That is absolutely a mindset I have.
Yeah, just be open-minded. Be willing to, ask why. Whenever you know something, like you come across something you don't know, like make a question out of it. Ask someone. If they don't know, then ask someone else. Rely on your teammates too. Like you can't do all this stuff alone. Like we mentioned earlier, this thing is way above any of our individual capabilities, and we need to work together to make it work. Teamwork makes the dream work. Just like with satellite constellations. They can't work by themselves, but together they do a pretty cool thing. So yeah, I would just encourage you to work with, lean on your teammates even, and just continue to be curious about this type of work.
Yep, leaning on your teammates is the best thing. Everybody has their own strengths, and of course it's best to build up your weaknesses, but you can build up those weaknesses by learning from those who are strong in them. And so asking those questions is the best way to do it.
Yep.
Well, thank you so much, and for your courage in doing this without, Dr. King here supporting you. He told me he knew you could do it without him, and you proved it to be true. So thank you, and thank you everyone for joining us. And we are in the middle of Winter Carnival here, so if you can imagine, I'm sure you have memories of Winter Carnival, but the big build night is Wednesday night, right?
Exactly. Yep. All-nighter.
Yep. All right. Thanks everybody for joining us, and we're signing out.
Thank you very much, Dr. Callahan.